Okay, students, I want to do something of chapter 16.7, but not completely, just to let you see how they come to certain formulas, and maybe you can do then with some. If you have some other problem with your other coordinates, maybe you can do exactly the same steps, and you get also that kind of results. First of all, let R be some point in the R2, and then we have there we have the XY space. So I want to work in the R2, just a space, the flat space, so no z-axis, and maybe if I want to make some sketch, it is easier, then we have some three-dimensional space. Now you have your x, y coordinates, and you have your and you can also use the polar coordinates. So, and now in a certain sense, the question is the gradient of f in polar coordinates. What to do? How to calculate it? That is the main question. And let me see how we can do that. Now, what do we know? We can write our R some point in the R2, and so we can write R as a vector, and we can write it as in polar coordinates. You get R times the cosine of phi, and that is times the I plus R times the sine of phi times the j. And now I can look for the direction of R and the direction of phi in the xy plane. So I want to know the direction of R and phi in the xy plane. Now what to do? If you differentiate that R to the radius, you get cosine phi I plus the sine of phi j, and I will make a sketch just over a few moments, and then we will see if that indeed gives the direction of R or the direction of phi. Now if I differentiate to phi, I get out of it minus R times the sine of phi times E plus R times the cosine of phi times j. Now, yes. Now, and let's see what happens. You have your xy plane. You have some point here, that is the R, and that R we see as a vector, so we take the origin and take some straight line to R, that gives you that vector, and then that vector has some angle with the positive x-axis, that vector has some length R, and in the direction of R that is in this direction. And what do you see? Indeed, it gives you the what we have calculated is good. It gives you indeed the, so you have here r cosine phi, r sine of phi, and that vector cosine phi, sine of phi, if you are in the point r and you go then in the direction cosine phi, sine phi, then you go in the direction of the r. That's no problem. Then the other one, the r d phi. Now what do we see? In the first quadrant the sine is positive, you have minus r times the sine of phi, so the x component becomes negative and the y component becomes positive, and it depends on r. So you have, and so yes, this r, that is the point, or the vector which you construct by going from the 0 to r, that gives you the vector. And then you have here the r, and then differentiated by the radius, and this vector here, that is the r, that vector differentiated by phi, that you have there. Now, what is of importance? The xy plane is anti-clockwise orientation. That is the orientation. And if I write down r phi, so first the component in the r direction and then in the phi, then you have also anti-clockwise orientation. So you have also to go, if you go from the r direction to the phi direction, you have also to go anti-clockwise. What do I see more? I see that if you take the inner products of those two derivatives, that we get a 0 out of it. So we have here r, and you take the inner product with that r differentiated by phi, we get a 0 out of it. And so those vectors are staying perpendicular to each other. That's of importance. And then we can also calculate their length. If you calculate the length of the r, it is the vector differentiated to the radius, you get 1 out of it, and the other one, if you differentiate it to phi and you calculate the length of it, you get r out of it. This is called the scale vector belonging to the radius, and this is the scale vector belonging to phi. So we have here scale vectors and important facts. So scale vectors keep in mind, and see also that those vectors are staying perpendicular to each other, and also of importance was the orientation. Okay. Now what can we do? We can make unit vectors in the r direction, in the phi direction. So if you have now that if you take maybe I can better do what is written in Adams. They differentiate the vector to some parameter, and we have differentiated to r, and this is equal to the scale vector times the unit vector of r, and in our case becomes the unit vector in the r direction is nothing else than the cosine phi sine of phi. So that is the unit vector, and the other one, if you differentiate it to phi, you get that scale vector in the phi direction and then minus sine of phi cosine of phi. And so we have that the unit vector of the angle, then you take the derivative and you divide by its own length, or you can also say you take the derivative and divide by the scale vector. That gives you minus sine of phi cosine of phi. So we can also say that that unit vector here, that is 1 divided by the scale vector times the partial derivative of r d phi. And this we can also write down, and that you see also somewhere staying in Adams. Okay, so r and phi, yes, those vectors, unit vectors and orthogonal. Now, because those vectors are staying, those vectors are orthogonal, therefore therefore we are speaking here about orthogonal coordinates. And that is nice, because if you have their orthogonal coordinates, you can also calculate inner product, you can calculate lengths of vectors and so on. So you can do if those vectors would not be perpendicular to each other, it would be very difficult to calculate. You can nothing say if they are staying perpendicular or something. You cannot define some inner product, or an inner product doesn't say anything. So that is very important, that those vectors are staying perpendicular. That is the reason why. So therefore, if you go from the XYZ space to another space, you like it when that other space has also coordinates, directions of the coordinates which are perpendicular to it, so that the vectors are perpendicular to each other, and that they have length 1. Now length 1 can also always be given. Now not to say, but then you need you need a length, so there has to be calculated some length, and that is important that can be done. Okay. Now, maybe we can we have that formula dx dy is r dr d phi, and maybe we see here something in it, and that I mean with something that we we see that R, that is the scale factor of so you can also write in the form of the scale factor of R times the scale factor of phi, and then dr d phi. Right, so you have this one was the scale factor of the phi direction, and there is staying 1 times that one, and the one which is staying here, that is the scale factor in the radius direction. So here you see those scale factors are coming back, and we have already seen them, but here you, and this was for the ds term, so a small surface, a small part on the xy plane, and then the area of it. So okay. Now so now we have already we have some yes, so we know now those unit vectors. We know that they are staying perpendicular to each other. Now, and now we come to the question of the gradient of the gradient, what to do. Now, what can we do? We can do the following. We have the xy plane. We can there is walking some curve somewhere in it, and that curve, points on the curve, we can parameterize by the arc length. And so let this be a curve, and that curve is parameterized by the arc length. Now, if you do so, if that is the x and the y are parameterized by the arc length. If you have are then on some point of that curve and you differentiate to the s variable. So if we calculate this one, this is a tangent curve to the tangent curve to the curve, and that is of importance, and the velocity, the length of that tangent vector will always be 1, and that is of importance. So you parameterize by the arc length, and if you do so, then you have that the velocity vector, so the tangent vector along the curve, it has always length 1. So, and that is of importance. Later I will let you see that indeed it has that will always be the length is always 1, but not now. Okay. Yes, what to do now? That curve, if we use polar coordinates, we can parameterize the radius and we can parameterize the phi, and then I can ask myself the directional derivative of f along c. Now, what do we know about directional? No, that yes, this. Um, that is now our question. Directional derivative along C, and our function f is given by the r and the phi. That are the variables you have to fill in to get a value for your f. Yeah. Now, if you this is your function, so that goes from the R2 to the real numbers. Now we fill in the curve and we differentiate the whole thing. So we have the radius depends on s, the phi depends on s. Now, what can we do? The only thing how we can calculate it is by taking the partial derivative of f, and then you get times the derivative of r plus, and then you have the derivative to phi, and you fill also the coordinates of the curve times the derivative of phi. So this is your df ds. In that curve. Yes, that is your df ds. Your derivative of f in that point along the curve. But this one, this is the same as the gradient of f inner product with the unit tangent vector. And yeah, that is the same thing. And how will that look? Now, I want to write that gradient as a constant times something in the r direction plus something in the phi direction. So I want to write my so I can try to write my my gradient. And my gradient is some vector in the R2. I have some unit vector, so I can try I can rewrite that function with two variables as a combination of the unit vector of r and the unit vector of phi. Further, the tangent vector along that curve that is equal to, now what do we have? You get there the derivative of r times the unit vector of r plus, and then you have r times the derivative of phi times the unit vector of phi. Be careful that you have this one here is of importance. Don't forget this one here. Now, and if you now calculate that inner product of that function of the vector with the unknown c's with that tangent vector, now we know that those unit vectors are staying perpendicular to each other, so the inner product of these two will always be 0. And what do we get out of it? We get then out of it C1 times the derivative of r plus, and then we have C2 times the r times the derivative of phi. That is what we get out of it, that directional derivative. And this is the directional derivative of dus in the direction of that c of your function f. And you have here you have the unit vector. The length of that vector is equal to 1, so a unit vector, and you know from that you have then the bidirectional derivatives, you have always the direction of your vector has to have length 1. Now that has length 1 here, so you have there the directional derivative. Okay, and we have also that we have also written, also already calculated some expression for that dfds, for that directional derivative, because that we have already here. Sorry. Here I had already calculated it, so here comes out of it the function f differentiated to r times the derivative of r plus the partial derivative of f to phi, and then you get times phi accent. Now look, what do we see? We get out of it c1 times the derivative of r plus c2 times r times the derivative of phi. Well, let me just make some steno of it. So c1 times the derivative of r plus c2 times r times the derivative of phi. That has to be equal to the partial derivative of f to r times the derivative of r plus the derivative of f to phi times the derivative of phi. And so you see, because those vectors have both length 1, the direction, we see now that we have here that c1 has to be equal to that partial derivative of r, and we see that c2 times r has to be equal to the partial derivative of phi. So here we have c1 becomes equal to the partial derivative of f to r, and c2 times r becomes the partial derivative of f to phi, and so c2 becomes equal to 1 over r times the partial derivative of f to phi. And so we see that the gradient of f becomes equal to, now the function f, you can calculate the partial derivative of r and then multiply it by the unit vector in the r direction, plus 1 over r times the partial derivative of f to phi times the unit vector in the phi direction. And so you have, so if you have now a function of r and phi, here we see what we have to do to calculate its gradient. with the variables r and phi. Now, and so you can do with a lot of other variables, you can also do the try to get the same results and almost the same idea as what I'm doing here. Constant, and what is of importance is that that curve is parameterized by its arc length. Now, if you have some parameter t between a and b, you can calculate the length along a curve, and that will be greater or equal to 0 and less or equal to L. And if your curve is parameterized by t, then the length along the curve is the integral from 0 to t, and then you have to calculate the derivative of the length of that vector, and you integrate it over the z variable. If you fill in, you get the length, you get the arc length. Now, let me call the function from t to the arc length L, and the other one goes back from the arc length to t. So those are L and T are it's inverse to each other, and so then we have the L of the B of t. No, that's not B of t, that's the S. So you have here an S, and you let L work on it, you get the B of S. Let me do the right thing. So this one I call the L of t, and going back I call the B of S. Now, so if I let B work on S, it becomes t, and if I let L work on it, I get S back. And so I see that if I differentiate it, that the derivative of L times working on B times the derivative of B becomes equal to 1. Okay. Then we have that parameterization. Now, if we parameterize by S, we can calculate the derivative to S. And what to do? There is here, in certain sense, staying the derivative to S of yes, and we can calculate the derivative to t, and then we can do the L of t, and that becomes the velocity vector. Nee, the vector, that's the tangent vector along the curve times the derivative of L. And yes, and the L accent of t. Now, if you calculate here you have the L of t, not L of t. So yeah, and then if you take the derivative of that L, you get the length of that vector out of it, and so we have that the derivative to S of xs becomes equal to the to the to the derivative of x divided by the of the L of s, L of t I mean, divided by its length. And L of t, that was s, so we have just the here the s, and here you see a vector with length 1. And if you calculate this length, you get 1 out of it. The last one I have done a little bit fast, but that is just to see that if you take the arc length for your parameterization, and so this is your arc length, so if you take your arc length for parameterizing some curve, if you calculate then the tangent vector along that curve, that has always length 1. Therefore, you see in Adams that if you read that chapter, you see that they use parameterizations with the arc length, just because then is the velocity, the tangent vector has always length 1. That is of importance. That is the important one. Thank you. This is not so. Yeah, this could be better. I could have better done than what I've written down here. But it's just to see from parameterizing by your arc length, then the velocity vector will always have length 1.